All right, so the recording has started. So again, on recording, I welcome you to this second part of this course, CH2101. And as I said, I will try to give you in the next 12 lectures or so, try to give you the very basic, to try to discuss the two very basic topics of organic chemistry, just to give you some glimpse of organic chemistry, because in first year it was really little organic chemistry, and also the next real organic chemistry course will come in the next semester. So it was decided to give you some idea of some basic idea rather of organic chemistry. So we introduced these little two topics in this advanced in organic chemistry course. And I'm sure you guys are missing campus, and we are also missing you. I'm also sure that for most of you, it's going to be the first campus live, and you are really eagerly waiting to come here and see ISER physically. And it must be excited, but considering the current situation, is it's not feasible at this point, and it's the best way to teach online. That is what we are doing. It's not really we are liking it. We also would like to see you physically and take live classes, rather physical classes. But what to do? So we'll continue online for the next 12 classes. But instead of making really online with PowerPoint and everything, I thought to give you at least some glimpse or some touch of classroom teaching. That's why I will mostly teach you in this board. It's a blackboard. It's actually in ISER we don't have blackboard. Rather, it's a very dark green board. When you see, you will see it. When you will come, you'll see it. And so I'll mostly teach the first part, at least, in this classroom teaching with chalk and board. And the second part, the second topic, I will try to cover through PowerPoint and PDFs. So now let me share my screen for just for a few minutes, and then we'll switch to this blackboard teaching. I believe my screen is visible, right?
Yeah, sir, it's visible.
All right, thank you. It's just copy pasted from the website. So this is my part. I am going to teach you around 12 lecture, as I said. First will be the aromaticity, which will take around 4 lectures. And second part will be the stereochemistry. That will take around 8 lectures. I'm not going to read all these things here. It's already there in the website. So we'll try to cover all these topics starting from here and up to the end. All right. And in the aromaticity, we'll cover these things. But actually, there is not much connection in between these two topics. The stereochemistry and aromaticity, these are different topics. So I thought to switch these two, although in the syllabus is written that aromaticity first and stereochemistry second, but I thought to switch. So what we'll do, we'll first discuss the stereochemistry part. It will take around 8 lectures, and then we'll come back to aromaticity. And for the stereochemistry, it will be exclusively in this blackboard teaching. And for aromaticity, I will majorly use PowerPoints and PDFs with writing on that PowerPoint and so on. All right. So that's the thing. And in between, of course, I will take one quiz, and only one quiz I will take in between. I will announce the date. It will not be a surprise quiz. It will be an announced quiz. And then, of course, at the end SEM. And we'll also announce the weightage of my part and Professor Arinda Mukherjee's part just before the end SEM. We'll announce, and then you can prepare yourself accordingly. And for the study material and books, I would say most important is that you sincerely attend the classes. And of course, I will record this thing because probably not all of you have very good internet connection. So of course I will record and then put it in the YouTube. It's best, of course, you attend the classes. If not, in cases you cannot, then you go back and then check the YouTube links and then watch the video carefully. And time to time, I will send you some study materials, some PowerPoint, some PDFs. You read those, and also I'll give you homework, assignments, also sincerely and seriously do those things. These are the most important things. So if you do that sincerely, I don't think you really need some additional thing. But if you are really interested, of course, I recommend you to read these books. For stereochemistry, is the Nasir Puri book. This is an Indian author. So he wrote a very nice book. It's also available in Google Book. I will send you the link for that, this Google Book. It's the language is quite simple and interesting. You can read this. And the second one is more advanced level, I would say, is from Professor LEL, who is the pioneer or the father of stereochemistry. And but I personally feel the language is a little bit tricky and a little more difficult. So the Nasir Puri book I personally prefer, but you can always read both or this one as well. And the third book is a general organic chemistry book. It's by three authors, Clayton, Gravis, and Warren. But it's mostly famous with the name of Clayton book. Probably some of you already know the name. The Clayton book, very nice general organic chemistry book with very colorful structures and very nice. I also personally like this book. There is a chapter dedicated for stereochemistry. You can read this too. This book also, the e-copy also available in different sources. You can have that, the PDF, or you can buy the hard copy. If you are thinking to take chemistry as major, I recommend you to buy this book. It's a very nice book. All right, but first, this is general, as I said, general organic chemistry book, or the first one, more specific, stereochemistry book. So this is the only PowerPoint I thought to show you for the stereochemistry part. For aromaticity, we'll come back, but there is a second slide. I'll come back in a minute. But let's first start with the Blackboard discussion. So at this point, I'll stop sharing and then go back to the Blackboard. All right, let's start. I believe the board is fully visible. So, as I said, we are first going to discuss the stereochemistry part, and it's always good to just before learning any topic, always good to know about the history of that topic. Right. So any topic, so history of this topic. So as we are started learning on stereochemistry, then it's better to learn at least briefly the history of stereochemistry. All right. And the thing is, you'll be surprised, although this is stereochemistry, of course, chemistry, you'll be surprised to know that the beginning of stereochemistry or the very early discoveries or kind of the basis of the stereochemistry was not discovered by chemists. So rather, it was a different physicist who laid the base of stereochemistry, and then based on that, chemists started or originated the topic of stereochemistry, and which is we are going to discuss over the next few lectures. Okay, and actually it's not not only for stereochemistry, for any scientific discovery, if you consider. So it's not like if you just compare any scientific discovery by climbing from ground floor to first floor. Okay, so let's from ground floor to climbing ground floor to first floor is a scientific discovery, and there are 20 steps. And it's very rare, or rather impossible, for a single scientist to climb these 20 steps and reach from ground floor to first floor. It was always several scientists, is the effort from different scientists who, suppose first scientist, he climbed only first 5 steps, And from there, the second scientist took over, and then like 5 more, and so on and so forth. And ultimately, with the combined effect of 4, 5, or multiple scientists, they reach from ground floor to first floor. That means one big scientific discovery happened. So in case of stereochemistry, exactly happened the same. Okay. So let me discuss that. So it was started with this discovery. So you can imagine, this is nothing but normal light. So as you know, in normal light, these electrical fields are oscillating in different directions randomly. So one scientist, his name was Huygens, he was a Dutch guy. He discovered that if you take this normal light and pass through polarizer, this normal lights where the electric fields are oscillating in different directions, it started oscillating in a particular direction. Okay? And these lights kind of called the behaved light, or in more scientific term, plain polarized light. So in short, I will write it PPL, plain polarized light, where the electric field is oscillating in a particular direction. So no chemistry, only physics. He was a physicist, the Huygens, the Dutch guy. He discovered that. And he left it there. Yeah. So from there, another physicist, he knew the discovery of plain polarized light, and then he used that one, the plain polarized light. And his observation was, when he passed this plain polarized light through a solution of chiral molecule. Okay. So, as I said, this guy, the second guy, his name was Biot. He was, I think he's a French guy. He was also a physicist, so no chemistry here. But in nature, as you know, there are several chiral molecules. I think you know chiral molecules. If not, then I will explain in a minute. So he just took a random, naturally occurring chiral molecule, just mix it in a solution and put it in a glass tube and pass this plain polarized light through this solution. And interestingly, he found that the light which was oscillating in this direction, there was a sharp rotation. There was a sharp rotation in this pathway of the oscillation of this light, plain polarized light. Okay? Suppose the rotation is alpha. Okay. This was his observation. So that means if you pass this plain polarized light through a solution of chiral molecule, the plane of the oscillation don't remain the same. Rather, it rotates from the initial path length, and he just measured just the angle of rotation as alpha. Okay. So this was another discovery, the second step of stereochemistry. Although there is no chemistry yet, but this was just the observation. Okay. Now comes the third person. Okay. Third person was, I'm sure you know the name, the famous Louis Pasteur. Louis Pasteur, he took over from here because he knew that if we take plain polarized light and passes through this solution of chiral molecule, there is a rotation. Okay. But up to here, it was all experimental observation, no explanation yet. Okay, so Louis Pasteur took over from here, and what he did, he took this molecule. So any of you know the name of this molecule? This is the first molecule I draw in this course. Although I will draw many molecules. Any of you? No?
Tartaric acid.
Tartaric acid. Very good. So this is the acid from Imli, right? It's a naturally occurring in nature. And the thing is, as you can see, he took this tartaric acid. It's called as TA, tartaric acid. So what he did something weird, I'd say. He made a salt of this CO2Na H4 plus sodium. He made it sodium. Yeah, that's correct. This minus is just the salt. Okay, sodium and ammonium salt. He made it. He was a great chemist. He was everything, as you know. Louis Pasteur has a lot of contribution in everything. Even these days, still we say pasteurization. This term we are using for. I don't have to tell his discoveries, I'm sure, at least to this, to you guys, to science students. All right. So he made this thing, and what he did, he managed to separate from the initial salt. He managed to separate two isomers. He managed to separate two isomers, namely the plus tartaric acid and minus tartaric acid. Okay, this plus minus thing I will come in a minute. What is this plus minus thing? So from a mixture of this tartaric acid, he made this salt, sodium ammonium salt, and could manage two fractions. One is plus tartaric acid, one is minus tartaric acid. After this separation, what he did, he took first the plus tartaric acid and made a solution like this and passed a plain polarized light. And he measured this alpha, the amount of rotation. And he observed that the rotation here is alpha D is plus 12.7 degree. What is this this alpha D? I'll also come discuss at the end of this lecture. Don't worry. This is called specific rotation. But just look at the values. Okay, plus 12.7 degree the rotation. For the minus one, he repeated exactly the same, and he found here alpha D equal to minus 12.7 degree. That means the two components that he could separate from the mixture of tartaric acid, it's giving exactly the same rotation, same amount of rotation. Okay? But in both cases, this is 12.7 degree, but the direction is different. Okay. He was really excited, and it was a big discovery. It was for the first time two chiral component was being separated experimentally, and it was measured and found that these two chiral components from one mixture give same rotation but in opposite direction.
Sir,
Yes.
sir, from what we have known from earlier that optical
Yes.
optical means isomers have same chemical properties. Only they differ in optic means this rotation. So how did he even separate it? How
By
did he separate it without knowing?
He separated by crystallization. I agree with you because in later part of this course we'll discuss on this resolution thing. So it's not easy, but he could manage it. So normally it's really need another chiral information to separate these two. You are right, but it was a special case, I would say, because of this making of this half salt, I don't know, that's why probably he was working on this for a long time, and fortunately found when there was a special case, as you can see, is half sodium and one ammonium. It was a really special salt. It's not like both are sodium or both are ammonium salt. With this half salt is special case, he could manage to crystallize out these two. Okay, so I agree with you. It's separating two enantiomers are not that easy, but as a special case, he could manage, and it was the first time, at least first time for the known or documented in literature, that separation of enantiomers. Okay, but this resolution and the optical properties and everything will come, we'll discuss in these 8 lectures. So don't worry. Okay, so we'll discuss in more details. All right. So he could separate and then measure and found that the rotation is exactly same but in opposite direction. But you see, still this one is experimental observation. No theory yet, right? No theory, all experimental observation up to here. And but all these interesting discoveries or experimental observation really triggered people to come up with some theory. And finally, in 1874, so the Louis Pasteur's observation, it was in 1849 here, 1849. Okay. So almost 25 years later, actually exactly 25 years later, 1874, at least some theory came. And the theory was given not other than Van 't Hoff. So Van 't Hoff and one collaborator of him was Lebel, Van 't Hoff and Lebel. They finally came up with some theory, or we can say it's not really, it was basically a hypothesis that probably it's happening. So let me write that. Basically, there was 2 statements they gave. They gave that carbon with 4 bonds is tetrahedral. Carbon with 4 bonds is tetrahedral. Okay. And the second statement was such tetrahedral carbon may exist as a pair of isomers. Such Okay, so I repeat these 2 statements. Carbon with 4 bonds is tetrahedral, and second statement is such tetrahedral carbon may exist as a pair of isomers. Okay. So they gave these 2 statements to explain this phenomenon, that from a mixture of tartaric acid, if you separate 2 fractions and you put it in the plane polarized light, passes through, and then there's a rotation, and then there's a rotation is exactly same and in different directions. Okay, so that means there must be something. These 2, whatever they have separated, these 2 are not same. That means these 2 are different. And Van 't Hoff said and Lebel that the difference comes from the tetrahedral geometry of carbon. Because all are organic, of course, we are in all these lectures, we will discuss on the stereochemistry of organic compound. And organic compound means, of course, carbon. And this carbon, they said, carbon with 4 bonds are tetrahedral. Because with 4 bonds is different geometry are possible, right? So it can be planar with just plus sign like this. They say, no, it's not plus sign, it's not 2D. Rather, with 4 bonds, it's tetrahedral, that means it's 3D. And this tetrahedral geometry is the origin of this difference. Okay, that means with the tetrahedral geometry, it may exist as a pair of enantiomers or isomers. They did not use that term enantiomer at that time. They just say isomers. And this was kind of the first theory to explain all these phenomena, or to explain the different properties or different divisions or different things in stereochemistry. But there was a first theory, and from there many other people took over, and then they study on stereochemistry and the birth of stereochemistry, whatever we'll discuss, all the phenomena started. Okay. So let us first discuss this Van 't Hoff's theory, or this hypothesis, because there was no experimental evidence at that time. They just gave a kind of a hypothesis, right? That's why they said may exist. But of course, later on people proved that yes, these are true, and that's the origin of stereochemistry. So let me explain or discuss this thing in more details with these models. In this course, time to time, I will show you models, because this is the easiest way or appropriate way to discuss stereochemistry. Without model, stereochemistry is not really complete. And also, I request you to draw molecules, okay? So if you, without drawing molecule, you cannot learn stereochemistry. That is very important. And believe me, if you just follow my instructions and draw molecules after these 8 lectures, things will be much easier. And the fear of stereochemistry or organic chemistry, if there are any, will go away. All right. So that's the thing. So the first statement, carbon with 4 bonds are tetrahedral. So this is a perfect example. You see, this is not 2D, it's rather 3D and perfectly tetrahedral. One carbon, the center is a carbon, and 4 bonds. And as he said, carbon, this is another one. Basically, it looks the same, right? So another carbon with 4 bonds and tetrahedral geometry. Both are having red, blue, green, and white bonds, atoms at the end. So apparently it looks the same. But the thing is, as Van 't Hoff said, that carbon with 4 bonds with this tetrahedral geometry may exist as a pair of isomers. So isomers means what? Isomers means it's same chemical formula, but it's different, right? Same with 2 molecules with same chemical formula, but these 2 are different. So as you can see, there is a central carbon and then 4 atoms at the terminal, red, blue, green, and white. So these 2 are isomers, there is no doubt, but we have to check whether these 2 are different or this is the same. To check that, let us try to merge these 2, okay? So how to merge? Let us mix this blue with blue, this blue, and red with red, and the central carbon as well. Okay, so let us hold it like this. So I merge this blue with blue, and this red with the red, and the central carbon. Okay. So then let us check what's the fate of the other 2. Let us hold this like this, then it's better. So I merged blue with blue, red with red. What's the fate of the other 2? You see, then this white and green, these 2 are not matching, isn't it? These 2 are not matching, although blue and blue matched, red and red matched, central carbon also matched. These 2 are not matching. That means these 2 are not same. Apparently, it looked like it's same with four same atoms around it, but it's not the same. Okay. So basically, these 2 are enantiomers. In a minute, we'll discuss that. All this division, enantiomers, diastereomers, all these things. But so this proves the theory, Van 't Hoff's second statement. The carbon with tetrahedral geometry may exist. So we'll just remove the may. So it exists as pair of isomers, or rather enantiomers. Okay, so it's exactly same like our hands, as you know. This our right hand and left hand, these 2 are not same. So if you try to merge these 2, it will never merge, right? So rather, as you know, our left hand and right hand are mirror images, right? So if you just imagine one mirror here, and then these 2 thumbs will be mirror image, and all other 4 fingers will also be mirror image, right? The same here, exactly same here. If you just hold it like this and just imagine one mirror here, you see? Oops, no. You have to hold it like this. Yeah, now it's perfect. Imagine the mirror here, you can see. that this blue will mirror image, green will be mirror image, red will be mirror image, and this white is which is away from the mirror also be mirror image of each other. Okay? So you agree, right? These two are mirror images and these two are not same. Okay? So that is the very basic principle of organic stereochemistry. That means carbon with tetrahedral geometry, that's the origin. And because of the different orientation of the atoms around this tetrahedron, it generates different isomers. And that's the origin of stereochemistry, all the properties of all the phenomena, everything. All right, and that's the brief history, starting from the plane polarized light with the three different experimental observation, and then finally the theory came, and then it's rolled over, and then all the theory, all other theory and all the things came. Okay, so now let us discuss in more details this part. So next we'll discuss the division, okay, the division of stereochemistry or the classification. To discuss the classification, let us start with the term Van 't Hoff used, that the isomer. So Van 't Hoff never said enantiomer because it was not known at the time. He said rather isomer. So let us start from isomer. So what are isomers? What's the definition of isomer in one line? As I already said, no? Molecules with same
Similar
chemical
structure.
formula. Exactly, same chemical formula. So isomers are molecules with same chemical formula. Now, if you see the classification or division in isomers, there are two. One is constitutional isomer. Another is stereoisomer. Right. So constitutional isomer is nothing but molecules with same chemical formula, but the connectivity is different. Okay? So the atoms are, the connectivity of the atoms are different. Let me give you one example. Let us take C1 formula, C2H6O. Okay. So can you please name one molecule with this chemical formula?
Sir, ethyl alcohol?
Yes, ethyl alcohol.
Very good. My favorite molecule, ethanol. CH3, CH2, wait, right? One more?
Dimethyl ether.
Very good.
Dimethyl ether.
You see, the connectivity of atoms, of course, not the same. Here, oxygen is at the terminal. There is a carbon-carbon bond. Here, there is no carbon-carbon bond. Oxygen is coming in between. Of course, these two are constitutional isomers. But in case of stereoisomers, it's not the case. Stereoisomers, same connectivity. But here the difference coming from the arrangement. Okay, the connectivity of the atoms is same, but arrangement of the atoms are different. If the molecules are isomers, having fulfilling this criteria are called stereoisomers. And of course, this next 8 lectures will focus on these stereoisomers. Okay, so now in stereoisomers, there are also divisions. There are 2 major divisions. One is optical stereoisomer, another is geometrical stereoisomer. Geometrical, another is optical, right? Geometrical and optical. Geometrical is more simple. Let us first discuss that one. So from the name itself, you can guess geometrical means the origin is originated, must be something from its connection with geometry. Let me give you the example and things will be more clear. This guy here, methyl HH, okay, which is nothing but trans 2-butene, 4 carbons, and there is in between one double bond. 2 methyl groups are there in the terminal, but away from each other, opposite direction. That's why it's trans, of course, as you know, trans 2-butene. Okay. So if you compare this with this guy, where 2 methyl groups are in the same side, which is cis isomer. Okay, so then this trans 1 and cis 1, you will say these 2 are geometrical isomers, or rather more specifically geometrical stereoisomers, because you see it's fulfilling the same chemical formula, same connectivity, but the arrangement of methyl groups or the hydrogen groups are different. In one case, these are diagonally opposite, and in one case, it's in the same direction. So the geometry is different. That's why it's called geometrical isomers. Right? There can be other examples also. Let me draw it somewhere here. Have some space.
Sir,
Yeah. Yes.
sir, actually, I'm facing one problem here that in stereoisomerism, as you say that same connectivity but different arrangement. So means connectivity means what? Means atom to atom that is connected, right? Means carbon is connected to methyl over in trans and in carbon hydrogen. So it's getting different. So how it is coming to be a same connectivity? That's
Okay. Very good question. So I'm glad that you asked this. Okay, so the connectivity means, forgot about stereochemistry and everything. You just write it like, I'm sure when you started writing the organic molecules in the school level, probably class 10 level or thing, in high school, then you started writing like this, no? Suppose this one, carbon like this, another carbon, and a double bond, another carbon, right? And then another carbon like this, and then you fulfill the valency, just putting hydrogen, 3 hydrogen here, 1 hydrogen here, 1 hydrogen here, again 3 hydrogen here. Okay. So just forgot about the stereochemistry, forgot about the geometry, to write like this. Okay. So you will get like a connectivity of atoms, right? There's a carbon, then carbon, then carbon, then carbon, and this with 3 hydrogen, 1 hydrogen, 1 hydrogen, 3 hydrogen. So tell me, if you write this, follow this thing for trans and also for cis, these two will be same or different?
So the connectivity now, if I understand, it will be same, I guess, because
Yes.
the carbon, yeah.
Yeah. So that's the thing. That's the thing. The connectivity of atoms. Okay. Carbon, 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 and this is with 3 hydrogens. Middle 2 are with 1 hydrogen, and the last one also with 3 hydrogens. These are the connectivity of atoms. Okay. These are same in both cis isomer, also in trans isomer. But if you compare here with ethanol and dimethyl ether, then you see it's different, right? Carbon, carbon, oxygen. Here, carbon, oxygen, carbon. Connectivity is different, isn't it? So
Yes, sir. Yes, sir. Okay.
that is what I mean. So where the connectivity of bonds is same, but the arrangement is different. Okay. So in this particular case is geometrical arrangement, that in one case two methyl groups are diagonally opposite. In one case, these two are in the same direction. The geometry is different. That's why it's called geometrical stereoisomers. In all stereoisomers, the connectivity must be same. That means if you write, like we just forgetting about stereochemistry, geometry, if you just write like this in a high school level writing, then you will get the same thing for all the stereoisomers. Okay, that's the easiest way to judge. All right. These geometrical isomers, it not necessarily has to be with double bonds. Probably people just think that with only with double bond, this cis and trans thing may come. It's not true. For example, in cyclic systems, let me draw two molecules. Let me take more space and draw it here. Suppose this cyclobutane, cyclobutane. Here also, you can have cis trans, methyl, hydrogen, methyl, hydrogen. Okay. I don't have a model, unfortunately, but if you have problem in understanding, I can build a model and show you in next class. So suppose cyclobutane. Let's take a duster, although it's not square. Pardon me. Just imagine that it's a square like this, and then this with the carbon, the bonds, one methyl can go up and hydrogen can come down, and then if I put another substituent in the diagonal carbon, so then there's a two possibility that this methyl can be in opposite direction or it can be in same direction. So this is also related to geometry.
Sir, are all four carbons of the square in one plane?
Yes, these four, the cyclobutane ring we are considering as a planar. Okay. Cyclobutane ring we are considering as a planar, and then we are just, because the other carbon are not having methyl groups, these are having hydrogen, both are hydrogen, 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 hydrogen. Okay, that's why we are not drawing, we are not making it more complicated. Only two carbons are having methyls here and this. The two possibility that two methyl groups can be opposite direction, or two methyl groups can be in the same directions. Okay, so there is nothing related to any double, there is no double bond, but still these two are geometrical isomers or stereoisomers. This will be called trans, this will be called cis. Okay. Very similar to that, but these are not planar. So for geometrical isomers, stereoisomers is not necessarily that has to be planar. In the main part, methyl group anyway is not planar. The main part I'm telling. It can be like this, but there is no double bond, but it still can possess geometrical isomers, trans and cis. Okay. So I will make a model maybe in next class and show you. But do believe me at this point that this is also possible. Okay. So these are the story of geometrical isomers. Let's come the most important part as the optical isomerism, optical stereoisomers. Okay. In optical stereoisomer, we need more space. So let us come here. What is this optical isomers, and from where this optical name came? Actually, optical isomers came from optics, and that means light, and from mirror. Okay. This optical isomers is nothing but the stereochemistry of mirror images. All right. So at the beginning, just for explaining the theory of Van 't Hoff, we have discussed with these models. Let us come back to this. as I said, for this understanding these optical isomers, you need to think about the mirror images. Suppose you have one molecule like this, okay, and you just hold this in front of the mirror, and then whatever you see in the mirror, you build up another molecule. Okay, so the mirror image, you make another model. So that is what we made here, right? So this, as you have seen, that these two are mirror images of each other. So if you just see the mirror and then you make a model, so it will end up with this one. So these two are mirror images of each other. And then you have already tried to superimpose, and have found that only two atoms can be mixed. And then the other two will never mix. So green, any two, you mix green and white or whatever, green and white, but then green and white we mixed, but then other two, the red and blue, will not mix. Okay, so these two are not same, but these two are mirror images. So that was the origin of the optical stereoisomerism, and the definition comes like this. Okay, so these two molecules that we discuss with the model, that these two are non-superimposable mirror images. So this superimposable is nothing but, is a more scientific term, the merging. Okay. If you first we make these two are mirror image, as we agreed, but when we try to merge these two, these are not merging. That means when we try to superimpose these two, it's not possible. So these are non-superimposable mirror images, these two molecules. Okay. And this kind of molecules are called enantiomers. Okay. So these enantiomers is the first one of the division of optical isomers. So in optical isomer, in geometric isomer, there is no more division. All are this cis trans kind of thing. But in optical isomers, there are also two divisions, right? One is enantiomer. So what's the definition of enantiomers, or the criteria to be enantiomers? It's non-superimposable but mirror images. Okay? So any chiral compound which is having non-superimposable mirror images will be called, these two pairs will be called as enantiomers. And the second one, this is number one. Number two is diastereomers. Okay. What is diastereomers? Diastereomers are nothing but, this is also coming from this optical thing. Non-superimposable, not mirror images. Okay. Here, non-superimposable, yes, but those two are mirror images, then enantiomers. But here, both are no. These two molecules which are non-superimposable as well as those two are not mirror images will be called as diastereomers. Okay, but keep in mind they have to fulfill this criteria, at least up to this criteria, that the connectivity must be the same, but arrangement will be different. Let me give you the example. Things will be more clear. Example of one diastereomer. Erase this part. Make some more space. Don't be afraid with the drawing. I promise that things will be easier after a few classes. Let's make loading and going here. chlorine, bromine. Okay. So we'll discuss all this kind of drawing in more details in future classes. But at this point, just know this much, that when this is, this is flying wedge, probably some of you already know. Flying wedge, this means up above the plane, and this dotted line means below the plane. Okay. So now compare these two molecules. In one case, these are, you see the connector. First of all, have to check whether these are really stereoisomers or not. You see the connectivity is exactly same. Methyl on methyl, then carbon, carbon, methyl, methyl, carbon, carbon, methyl, of course. And the second carbon is having one hydrogen, chlorine, and of course one hydrogen is there to fulfill the valency. And the third carbon is having one bromine, and the fourth, of course, methyl. Same here. First carbon methyl, second carbon with one chlorine and H, third carbon with one bromine and H, and then the fourth carbon is methyl. So connectivity of atoms are exactly same. Okay, but the arrangement is different, because here the chlorine is up, bromine is also up above the plane, but here chlorine is above the plane, bromine is below the plane. That means the arrangement, the space arrangement is different, and so that means we agree these are stereoisomers. Then you have to check whether it's geometrical or optical. You see here, the thing is, in case of to become the optical enantiomers, that to be, these two are non-superimposable. You can already see, because if you, I'm sorry, this is a little bit more complex molecule. Probably the model is better. I will also make a model of this in the next class. So if you try to just imagine, no, because in this course you also need to have some kind of imagination, because that is important. Stereochemistry is all about imagination. Of course, the model will help you in at least at the beginning to imagine the molecules, but with time you have to build up your own imagination, so that you just close your eye, you can see the molecule, or you just draw on a piece of paper, you can really see 3D, because everywhere, of course, we will draw in 2D, but we have to imagine in 3D. So that is important. So with time, you can build it for sure. Just think about it. You just take this molecule and try to superimpose or march on this. So this carbon chain, which is on the plane, will be marched, but this chlorine will also march, but the bromine will not march, because in this case, one bromine is above the plane, other case, another bromine is below the plane. Okay, so it's not possible that these two are non-superimposable, of course. And believe me, these two are not, of course, not mirror image. Rather, the mirror image of this will be this one. Methyl here, chlorine, bromine, where both chlorine and bromine is below the plane, because these two are above the plane. No, just think about the mirror here. If you put the mirror here, you see, then it will go below the plane. No, anything. So if you just stand in front of mirror, then you just think something, hold towards the mirror, you will see that is going opposite to the mirror. Yeah, just try it at home. Anything. So anything is above the plane. If you put the mirror here, that will reflect like it's below the plane. Okay. So these two are enantiomers. These two are enantiomers, but these two are actually diastereomers, because there is in one case chlorine is up, another case bromine is down. In one case, both chlorine and bromine is up. Okay. So this is fulfilling the second one. These are the connectivity is of course same, but this non-superimposable and of course not mirror images. So that's why these two are diastereomers. So this the judging of enantiomers and diastereomers will be much easier when we will discuss all the drawing. Basically, these are called different projections. We'll discuss in more details, different kind of drawing, different kind of projections in future classes. But that's the major classification. Just to recap before closing the first class: isomers, two divisions, stereoisomers, and this constitutional isomers. And within stereoisomers, of course, there are two. One is geometrical, one is optical. Geometrical comes from geometry. These are cis trans thing. And in case of optical, there are two divisions. One is enantiomers, and another one is diastereomers. Enantiomers are superimposable but mirror images, but diastereomers are non-superimposable and non-mirror images. One last thing, the thing is here is all these geometrical isomers, no? These cis trans, all geometrical isomers, these are also diastereomers. These are also diastereomers. Keep this in mind, because this is also fulfilling this criteria. This, if you see, just draw on a piece of paper one trans 2-butene and hold it in front of mirror, you will see you will never get cis 2-butene. Okay, so that means you will see that trans 2-butene will show only trans 2-butene, not cis 2-butene. That means cis and trans, these two are not mirror images, and of course these two are not superimposable. If you take trans butene, it cannot merge with cis butene. That's why this is also fulfilling the criteria of diastereomers, not superimposable, as well as non-mirror images. That's why these are also called diastereomers, but those are geometrical diastereomers, not optical diastereomers. Okay? Diastereomer are of two kinds, geometrical and optical, but enantiomer is only possible in optical. So geometrical enantiomers is not possible. Only optical enantiomers are possible. So that's why only enantiomers are only present here, this part, but diastereomers are present in both the categories. All right. Okay, so I will stop here. In next class on Monday, I will bring more models and things, discuss things in more details. But I believe you got the brief history and the classification of stereochemistry. In next class, we'll discuss on a little bit on optical rotation, and of course, with the models, we'll discuss more on this isomeric things. Right. So I will close here. I'll stop the recording.